Hello, hello, hello. Good morning, everyone. So we're gonna get started today with our warm up of the day. We have a lot to cover today, so we're gonna get started ASAP, and we're gonna try to move through this at a pace. So to get started, let's talk about a warm up. So in this particular warm up here, we are looking at an astronaut that is weighing 140 pounds on Earth. This is one of the few times where we will use the sacrilegious measurement called pounds, where we will use freedom units. Usually we use kilograms, but we will see why we're using pounds for this specific problem. So do I expect you to know this? Probably not, but I want you to think about this problem. So an astronaut weighs 140 pounds on Earth. If this astronaut weighs herself on the moon, what will the scale read? This is kind of interesting. I want you to think about it. You may do some Googling to try to figure this out if you are of that kind of personality, which is okay. But an astronaut weighs 140 pounds on Earth. If this astronaut weighs herself on the moon, what will the scale read? So I want you to think about that for a couple minutes. While you're doing that, there is a graphic organizer on Canvas that we will be following along for this set of slides. I would highly advise you open that up and go through it as we are moving through this set of curriculum. So that will be due. Well, it won't be graded, but it will be. I do want you to finish it because and turn it in by the end of the period. So there's a graphic organizer on Canvas that you should open and fill out. The first the warm-up problem is the first question on there. So there is a space for you to fill that. And then I want you to think about this. So an astronaut weighs 140 pounds on Earth. If an astronaut weighs herself on the moon, what will the scale read? We will move on in a minute or two, so make sure you open that graphic organizer, answer this question in there, and then we will move on. Again, we have a lot to cover here, so we won't be waiting for any stragglers. We have a numerical answer, very interesting. We have another answer here that is also good. Interesting as well. Some riddle type thing. I'll take another 30 seconds for you to answer this. Make sure you have that graphic organizer open and you are answering this question in there. And I will talk about this. So as we talk about this, oh, another interesting answer. Ah, I love interesting answers here. Okay, so here's what I want to see. Here's what I think is really interesting. Okay, so first off, we have we have a couple of numerical answers. We have one person who feels that this is some riddle type thing, or I'm like trying to trick you or something. This is not a riddle type thing. Don't worry. There is an actual physical phenomenon going on here, so it's very reasonable. It's very real. We have a few numerical answers. So the correct answer is 23 pounds. As you are, but we will talk about why. I do not expect you to know off the bat. But I did want you to think about it a little bit, and we will talk about why this is true. So, agenda for today. So, after we finish the warm up, we will move on to the main part of today, which is I'm going to introduce. I know we talked a little bit about Newton's second law, but we're going to do more of a formal introduction where we do more math involved, and then also very, very, very important, we will be talking about free body diagrams today. So today's lesson, if you're going to pay attention to one lesson all of the unit, today is probably the day you want to pay attention to. So I would highly recommend you do that. This class is all the classes should be uploaded onto YouTube, so you should be able to review this. Again, there is a graphic organizer for today on Canvas that you should finish and submit by the end of the period. So yeah, so we'll be talking about F equals ma and free body diagrams. And make sure you fill out the graphic organizer, submit it by the end of the period. In terms of assignments, we will be working on free body diagram practice problems that we will be starting today. You may be able to finish it today, in which case you can start working on you can continue working on the force data analysis. The due dates for both the free body diagram practice and the force data analysis, they are both going to be due Sunday, Monday. So before class on Monday. Yeah. The practice problems should not take you too long. So that's why I feel okay with having you do two of them. The practice problem should not take you too long. You may be able to finish it by the end of the period today. Okay. So let's talk about why different things might weigh different numbers on different planets and stuff. So weight is not the same thing as mass. So this is a very, very, very important concept that is easily mixed up all the time. Your weight, your mass, correction, is how much stuff you have. The amount of mass an object has does not depend on where it is or what forces are acting on it. It's just always the same. So if I have a lot of stuff, I will always have a lot of stuff regardless of where I am. That's mass. Weight is measuring the force of gravity acting on it. So in the force data analysis, when I give you that big Google sheet with all the forces, a lot of you were like, I don't know what this force represents. That's okay. That is measuring the force of gravity. That is measuring the weight of an object. It is not measuring the mass of an object. It is measuring the weight of an object. And as you saw from that data sheet, right, the forces and the masses are not the same. Because again, weight is the force of gravity acting on an object. And because of this, your weight of an object will change depending on its mass and, more importantly, where it is located. Because where it is located will change the acceleration due to gravity, which will mean that the force of gravity will also change, and that'll create a different weight on different items at different locations. So this is why an astronaut who weighs 140 pounds on Earth will weigh 23 pounds on the moon, because the force of gravity on the moon is 1/6 of that of here. So any object that weighs 6 pounds here will weigh 1 pound on the moon. So, and that is a measurement of the force of gravity. Whereas the mass of an object is just how much physical stuff it has, which remains unchanged wherever you are. That is very important. So as we talk about forces, we will want to talk about units. So in general, not in general, always, kilograms are a unit of mass, not of weight. So if I say this thing is 100 kilograms, I'm giving you a mass of an object. I'm not giving you the weight of an object. If I wanted to figure out the weight of an object, what I can do is I can find the force of gravity acting on it, which is something like this, where F is equal to ma. I will talk about how this goes in a second, but if you do this out, you'll get that force is measured in kilograms times meters per second squared. In other words, you can think about it as the units of force is the units of mass, which is kilograms, times the unit of acceleration, which is meters per second squared, and then you'll get this. And what we call a kilogram meters per second squared, we call that a Newton. But we'll talk about how you do F equals ma in the case of gravity. But this is just to show you where the units of Newtons come from. So this is very important as well, the units of force. All of this is super important, but I think I want to reiterate, the units of force is very important. 1 Newton, Newtons are the units of force, and 1 Newton is 1 kilogram times meters per second squared. If you are ever unsure of what a Newton means, remember that force is equal to mass times acceleration. So as long as you know the units for mass and you know the units for acceleration, if you multiply the two, you will get the units for force. Newtons, which is kilograms per meters per second squared. So to sort of give a quick recap, when we look at the weight of an object, we found the strength of the force of gravity acting on it. We also found the units of force in the process, and the units for force are called the newtons, or N, and 1 Newton is 1 kilogram times meters per second squared. In other words, the units of force is the units of mass, kilograms, times units of acceleration, which is meters per second squared. Just a quick recap. Should I summarize? Force is different than mass. Weight is different than mass. Weight is the force of gravity. Mass is how much stuff you have. Units for force are newtons, and 1 Newton is 1 kilogram times meters per second squared. And let me know if I'm moving too fast. I'm trying to keep this at a pace, at a pace. Okay, so what I really want to what I really want to differentiate is the difference between force and acceleration. So the force of an object is how much an object is being pushed or pulled. It is not how much an object is speeding up or slowing down. What is commonly misconceived, for example, gravity is a force, not as acceleration. There is an acceleration due to gravity, but that is not what gravity is. Gravity is itself a force. How much, how strong a force on an object is related to the mass of the object. The stronger the mass, the stronger the force. Um, Another thing that's also important is that acceleration of an object due to gravity is constant, and it does not depend on mass. That's within any given location. This is only true for gravity. In other cases, different forces will give you different accelerations. But in the case of gravity, the gravitational acceleration is always constant. It's always g 9.8 meters per second squared. So acceleration is always constant due to gravity. Force of gravity depends on the mass, and it's not the same as acceleration. As you can tell, because because the acceleration due to gravity is constant, what this means is that all objects will fall at the same rate, and you will see in a second what that means. So what I want you to do in your Google or your graphic organizer, there should be a space to answer these set of questions. So in this particular question here, I drop a coin and I drop a feather. So the mass of a feather is very small. It should say 0.012 kilograms. And the mass of the coin is 12 kilograms. So what I want you to do is find the force of gravity on the coin. So I will give you, so the force of gravity is, F is equal to ma. In the case of gravity, the force of gravity is F is equal to mg. So F is equal to mg is the equation you're going to be using to find the force of gravity. What I want you to do is I want you to find the force of gravity on the coin, find the weight of the coin, find the force of gravity on the feather, find the weight of the feather, and then talk about which one hits the bottom first and see if you can explain that. So we're going to answer these questions. We'll take a few minutes to go through this. If you're unsure what equation to use, so remember, we're going to use Newton's second law, which is very important, which is force is equal to mass times acceleration. In this case, we're dropping both objects. So the acceleration of an object is acceleration due to gravity, which is 9.8 meters per second squared. So you're going to use F is equal to mg, with g being 9.8 meters per second squared. And you're going to try to figure out the force of gravity on the coin, the weight of the coin, force of gravity on the feather, the weight of the feather, and which one hits the bottom first. And whenever you're ready, you can put your answers in the Zoom chat. Hey, what we could get. So someone just shared with me a really good video. So I will actually watch it real quick. Anyways, that should help you with one of the questions. But I think we've got a conceptual idea of how to do these. If you have mathematical answers for the force of gravity and the weights, that would also be good. I would love to see those if you do have those. If you are not sure how to do those, we will go over a more mathematical approach to force. The general equation we want to use is F equals ma, where force is equal to mass times acceleration. In the case of gravity, our acceleration is the acceleration due to gravity, which is 9.8 meters per second squared. I got one answer so far. Thank you, Charles. Charles, great job with units, by the way. That's I like to see when people nail their units. Great job there. Let's take another minute or two to go through and see if we can figure out more of a mathematical answers for these. We have already a couple people who have the decimal is off by one place. Oh, I didn't even notice that. Good catch. Excellent catch. So take about another 10 seconds or so, and then we will go over the next part. So we have a good math. I think we're sort of getting the mathematical approach. Thank you, Cole. We have some ideas on the how things will hit, which one will hit the bottom first. Okay, so to figure out the force of gravity here, we are going to take our mass, which is 12, and multiply it by our acceleration, which is 9.8 meters per second squared. So 12 kilograms times 9.8 per meter second squared is 117 newtons. And that is the same as the weight. So the force of gravity is 117.6 newtons, and that is the same as the weight. So the answer for the first two questions is 117.6 newtons. The force of gravity on the feather is 0.012 kilograms times 9.8 meters per second squared. So when you do that, you get 0.1176 newtons. So the force of gravity acting on the feather is what, 100 times less than that on the is 100 or 10 times less? Let's see. It's like, no, it's like 1,000 times less. So the force of gravity on the feather is like 1,000 times less than that on the coin. The force of gravity on the feather and the weight are both the same. They're both 0.1176. However, even though the force of gravity on the coin is 1,000 times more than the force of gravity on the feather, they hit the bottom at the exact same time. Why did they hit the bottom at the exact same time? Because we literally just talked about how the force is so much bigger. So it doesn't make sense that since the force of gravity is bigger on the coin, that they would hit at the exact same time. Well, the key thing here is the acceleration of both of them is the same, right? So if you are accelerating at the same rate, your position is changing, your velocity is going to be changing at the same rate, which means your position is going to be changing at the same rate. So it doesn't matter that the force is bigger, because the mass, if the force, even though the force of gravity is bigger on the coin, the mass of it is also bigger, which will in the end sort of cancel out. And so as long as the acceleration is the same, they're going to hit the ground at the exact same time. So if you want to be looking at how the position is changing, you want to be looking at the acceleration. The force does determine a lot the acceleration of an object, but it can be misleading here. If you want to look at the position, you want to be looking at the acceleration itself, Yeah. So to recap Newton's second law, the big idea we wanted to be talking about is that an object accelerates when there is a net force on an object. What does it mean to have a net force? So again, acceleration is the change in velocity over time interval, which means that if an object speeds up or slows down, or it starts from moving or stops moving, those are examples of acceleration, which means that you need to have some sort of net force acting upon it. What does it mean to have a net force? So this is the big idea here. So Newton's second law is F equals ma. It's better described, a more accurate description of Newton's second law is that the net force is equal to the mass times acceleration. So what you want to do to find out your net force is you want to look at the individual forces and you want to see if they cancel out or if they add together. And then after you sort of do all of the canceling and balancing out, you will figure out the net force. So in these two examples, the first example is there's one group on the right, they're playing tug of rope. The group on the right is pulling with a force of 300 newtons. The group on the left is pulling with a force of 300 newtons. So if you are pulling on the right with 300 newtons, and you're pulling on the left with 300 newtons, guess what? Your two forces cancel out. So your net force is 0. So basically the rope is not going to move. Nobody is going to move. All these forces are going to cancel out. And so the net force is 0, which means your acceleration is going to be 0. So you are not going to move. The forces are balanced. In the second example here, the group on the left, they got much stronger. They decided to start lifting. So the group on the left is now pulling with a force of 400 newtons. The group on the right is pulling with only a force of 300 newtons. So if you are pulling to the left with 400 and you are pulling to the right of 300, well, guess what? The group on the left is pulling a lot stronger. So there is a net force going to be pulled to the left. The overall net force is going to be 100 newtons to the left. The direction is important here. That's because if we pull 400 to the left and 300 to the right, it will cancel out partially, and there will only be 100 newtons left pulling to the left, and that will be the net force in this example. What this means is that when there is a net force, is that the forces are not balanced, which means that your acceleration is not 0. The key idea here is identifying, right? Forces can act in different directions, and we want to be trying to balance it out or subtract or add or whatever in order to try to figure out the net force. The net force will then allow us to determine the acceleration of the object, the actual acceleration of the object. So in your graphic organizer, and then when you do this, you can also put into the Zoom chat, I want you to figure out there are 4 empty boxes here. There's one empty box with a net force, and then there are 3 empty boxes for the acceleration of each of these objects. So what I want you to do is I want you to go in your graphic organizer, fill it out, and then whenever you're ready, just put your answers in the Zoom chat so I can sort of see how we're doing. So to sort of go over the examples here, the first example is you are pulling with a force to the right with a force of 5 newtons, and then you're pulling with another force to the right with a force of 10 newtons. When you combine them, because they're pulling in the same direction, the overall net force is going to be pulling to the right with a force of 15 newtons. Notice how the forces added together here because they're in the same direction. In the second example, you're pulling to the right with a force of 10 newtons, and then you're pulling with a force to the left of 5 newtons. Well, the 5 newtons to the left will sort of balance out 5 newtons on the right. I think you aren't sharing your screen or something that is, you can't see the examples. Oh, yeah. That is horrendous. Oh my gosh. Oh, oh, no wonder why things wasn't. Oh my God. Sheesh, sheesh, geez, Mr. Who, what are you doing? I don't know. Good question. Okay. In my defense, I don't know if you can confirm this. I could have sworn it was working earlier. I think I might have did something to unwork it. Okay, excuses. Oh my God, you're judging me so much. Now you're making me feel super insecure about myself. So what this probably means is that there's a lot of stuff. Okay, it was working here. Okay, thank you for confirming that, Galen. I could have sworn it was working earlier, and I think that explains why a lot of yeah. So okay. So because I probably you did not visually see what was going on, and I was talking to a blank screen. If is there anything that you want me to go over? Just so for reference, the slides are also available on Canvas. So if you want to go back and look at it, that's also okay. I feel like a fool now. Hopefully you were able to at least write down, at least hear what I was saying. So hopefully that at least made sense. I don't think we were, I don't think anything was too crazy. But now that you can actually see what's going on here, that means we can actually do the examples now. Wow, Mr. Who. Wow. Okay, so the first example here, okay, we have three examples, at three different forces. The first force, there's a force to the right with 5 newtons and a force to the right with a force of 10 newtons, which means that you have an overall net force of 15 newtons to the right. We have a force, for the second object, we have a force to the right of 10 newtons, and then we have a force to the left of 5 newtons, which means that these sort of balance it out partially. So there is an overall force to the right of 5 newtons, which I think sort of makes intuitive sense. So what I want you to do now is I want you to figure out the third net force. What happens when there's a force to the left with 5 newtons and a force to the right of 5 newtons. And then I want you to try to figure out the acceleration, the magnitude, and the direction for these three particular examples. The mass of the object is 10 kilograms. So hopefully that should be able to help you out here. Do you have to make your own drawings? Um, you can just, I mean, you can just use the same drawings here on the graphic organizer. Um, but you don't have to draw anything for this part. You just have to figure out the net force, the mathematical net force, and then the mathematical acceleration. We will do drawings later on, but for now, just figure out the mathematical net forces and the mathematical accelerations. Whenever you're ready, just put your answers in the Zoom chat. On your graphic organizer, there are 6 blanks. On the example on the slides, there's only 4 blanks. So if you do answer in the Zoom chat, just the 4 blanks will be plenty. So does anyone have an idea of what the net force might be for the third example? If you're pulling to the right with 5 newtons, pulling to the left with 5 newtons, what do you think is the overall net force here? This one's kind of interesting. You pull to the right with 5, and then you pull to the left with 5, and then so what would your overall net force be? We got a couple of answers so far. Got 3 answers so far. We got nada, 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 nada. Yes, you are all excellent. There is not a force. Why is there not a force, Mr. Who? Well, if I'm pulling to the right with 5 and then someone else is pulling to the left with 5, right? Basically, we all just sort of cancel each other out. We're all just wasting our energy because we're just both just accomplishing absolutely nothing, which sounds like a lot of things going on in life. And so because of this, the net force is 0. Yeah. So now let's take a look at the accelerations here. So we have 3 net forces, 15, 5, and 0. We want to find the accelerations in this example here. Remember that the mass is 10 kilograms, and that the equation we want to be working with is that the net force, F net, is equal to the mass times the acceleration. Charles has got an excellent idea of what to do. Galen dittos Charles. Great dittoing. Good job. Anyone else who has any other opinions on this? And then we will move on shortly after that. So this is the general idea is basically you just figure out the net force. You figure out where all the forces are acting, figure out the net force, and then you just use that to figure out your mass times acceleration. So that is in itself is not too crazy, I think. The crazy part is when you start looking at lots and lots and lots of forces and how you figure out how things balance and cancel out. So yes, the three accelerations should be 1.5 because your net force is 15 newtons, your mass is 10. So your force divided by your mass is 15 divided by 10, which is 1.5. So your acceleration is 1.5 meters per second squared to the right. Your second one is 5 newtons divided by 10 kilograms, so 0.5 meters per second squared. And then for the last one, your net force is 0, so your acceleration is going to be 0. Okay, so that is the base. That is pretty much what you need to know for your FNet. That in itself is not the crazy part. The crazy part is what you do when you are. Okay, so this one we are just going to quickly go over this. How much force must the girl use to hold the rock steady? So to quickly go over this, right? The Earth is pulling with some amount of force. So in order to pull it up, right, the girl needs to hold the rock with the same amount of force as the Earth's pull in order to balance out and have a net force. You can't see it again. Bruh. What am I doing? What am I doing? Oh, what did I do? I hit it. There we go. Okay, I hit it. I don't know why I did that, but I hit it. Okay, so now you can see the example again. So there's a girl, she's holding a rock, and the rock is being pulled down by Earth. So in order to hold the rock steady, the girl needs to hold the object with the rock with the same amount of force as the Earth's pull. So the net force needs to be 0. So the upward push force needs to be the same as the lower Earth pull push force. So that's just a general idea. Please don't tell me I hit it again. Okay. So what we are going to do now is I want you to, so this is the first example here. There's a space on your graphic organizer to do this. What I first want you to do is I want you to try to figure out what the forces acting on a book sitting on a level table are. So this is where physics starts to get very visual. There is a book on a level table, and I want you to try to identify the various forces that are acting on the book to keep it level. There is a space in your graphic organizer to do this. It should be example 1. I want you to try to identify what forces are acting on the book, how much those forces have to be. So you want to think about what is the net force acting on the book? Is there a net force acting on the book? If there is a net force, what does that mean for our forces? It would also depend on the mass of the thing she was holding. That's true. That is true. That is true. The main idea is that she just needs to hold the object with the same amount of force that the Earth is pulling it on. So if it's a heavier object, it means that she needs to apply more force to hold it up, which makes sense, right? If you're trying to carry a semi-truck, you need to apply a lot more force than if you want to keep a feather steady. So let's try to identify all the forces acting on a book sitting on a level table. So the thing you might want to think about here is that is the book moving? Is the book accelerating? In my world, I don't know about your world, but in my world, a physics book on a table doesn't really move at all. It doesn't even move. There's no acceleration, which sort of means that there is no net force. So if there's no net force, this is where things get kind of tricky. If there is no net force, it does not mean that there is no forces acting on it. That is not true. It just means that all the forces cancel out. Now, in general, in life, there is always the force of gravity. Always. You can try, but you can't really escape the force of gravity because the world revolves around, yeah, Earth is big and Earth has a lot of gravity. So in this particular example, right, there is a force of gravity pulling on the physics book, which theoretically would mean the physics book should start accelerating down. However, this is not actually what happens. The physics book is not accelerating at all, which means that there has to be some other force that is counteracting the force of gravity pulling it down. There has to be some sort of upwards force. And so the upwards force being applied, right, is how much force the table is applying on the book. So the book is not accelerating, which means the acceleration is zero, which means the net force is zero. So if I were to draw this out, it would mean that the forces on the book are balanced, which means that there is a upward force pushing on the book from the table, and then there is a downward force pulling downwards on the book from gravity. So if you were to draw this out, right, you would draw two arrows, one arrow pulling up, and one arrow pulling it down. The arrow pulling it down is gravity, and the arrow pulling it up is the table force. One thing that's also very important is that when you are drawing your arrows on a diagram, the size of the arrow, the length of the arrow does matter. Because the size of the arrow tells us how much strong the size of the arrow, the length of the arrow, no matter how I say it, is always just going to sound weird. So just apologize. I apologize for that. The scale of the arrow, there we go. That doesn't sound as bad. The scale of the arrow, the magnitude of the arrow tells us how big the force is. So if I were to draw a huge arrow for gravity and a tiny arrow for the table, that would mean the force of gravity is much bigger than the force of the table. The force of gravity is much bigger than the force of the table, which means that the object is pulling downwards. That is not the case. The object is not being pulled downwards, so you need to have your arrows of the same length. Okay, so the previous thing is what this kind of diagram is called a free body diagram. I will introduce it in a second, I think, but this is the general concept. This is what we call a free body diagram. It's very important. And as part of the free body diagram, in order to sort of talk about what just happened here, one of the main forces is the force called the normal force. So the normal force is that the force an object exerts, it's the support force an object exerts on another object. So when an object is in contact with another object, right, the support force being acted upon is called the normal force. And the normal force is perpendicular to the supporting surface. So how do we label the normal force? We label with F subscript N. Very important. That's how you label your normal force, F subscript N. And so normal force is basically the force that is pushing against an object to support it. So in the book example, right, you have a book that is being pulled down by gravity. So in order to keep it up, the table applies a support force called the normal force that keeps the book up. So that is called the normal force. So there is a force pulling it down, force of gravity, and then there is a normal force from the table pulling it up. And the normal force in this example was the same as the force of gravity. The normal forces can also be applied at, for example, if a person is laying against the wall is going to apply a normal force to the person to try to keep the person from falling through the wall. And that force is always perpendicular to the surface. The reason why this is important is because if objects, which we will do, if objects are on a ramp, the normal force is perpendicular to the surface of the ramp, not perpendicular to the object itself. So example, well, I mean it's perpendicular to the object because the object is on the ramp. But for example, if you look at the second picture here, the normal force is perpendicular to the ramp. Notice how it's at an angle, even though the force of gravity is pulling it downwards. And we will see what that looks like later on. But yeah. Okay. So now what we are going to do is now we are going to examine something called a free body diagram. A free body diagram. Free body diagrams for literally every single problem for this unit, you will always draw a free body diagram. Period. If you do not draw a free body diagram, I will be upset. Yes, you will. Yes, you will. If you don't draw it, it's an automatic 0. Probably not true, but you will draw a free body diagram for every problem because they are extremely important. Because you will, trust me, you will want to. If you don't believe me, if you start saying, Mr. Hu, I don't know what the forces are acting on it, I will say, did you draw a free body diagram? So free body diagrams are diagrams that show all of the forces acting on an object. So when you draw a free body diagram, what you're going to do is you're going to draw an object. You're going to draw it as a box. It is always a box. If it's a car, it's a box. If it's a house, it's a box. If it's a circle, it's a box. If it's a triangle, it's a box. Everything is a box. And then from that, you're going to draw arrows perpendicular to, or you're going to, not necessarily perpendicular, but you're going to draw forces coming out of the box, starting from the box and going outwards. And that shows which direction that force is pointing. The length of the force is going to be the magnitude of the force. Each force is labeled with a symbol. So, for example, the force of gravity we label with the symbol Fg. The normal force we label with the symbol Fn. And you're going to represent the object as a box and draw the force arrow outward from the box. So this example here, we have a free body diagram of this book. So in this book, the free body diagram looks like there's 2 arrows. There's a box and 2 arrows coming out of it, the normal force and the force of gravity. Okay, so here are 3 must-know hacks for FBDs, for free body diagrams, must-know hacks. So hack number 1, every single object you draw is a box, Every object is a box. Okay, I do not want to see very nice, very pretty drawings with colors and shapes and whatever. That's too much work. Every object is a box. What you also should do is you should identify the net force in the problem. Is the object accelerating in a direction? Now remember that moving is not the same thing as acceleration. If the net force is 0, if there's no acceleration, then all the arrows should cancel out. And the length of the arrows do matter because they tell us how strong the force is in that direction. Another thing that should be considered, that you should consider, is that just because an object isn't moving or accelerating in a direction, it does not mean that there aren't forces acting on it. So what you might be is, okay, you're like, okay, there's no net force on it, therefore there's no forces on it. That's not true because there's always the force of gravity acting on an object. In other words, gravity always exists. So you should think about what are the forces acting on the object that might keep it so that the net force is 0. So these are your 3 must-know hacks. First off, every object is a box. Second of all, you should identify the net force of the problem, and the net force of the problem should tell you whether or not your arrows cancel out. And last but not least, just because an object isn't moving or accelerating doesn't mean there aren't forces acting in that direction. Okay, so now we will cover all the remaining forces left. So one of the main forces we will talk about is the force of friction, which we label F subscript F, F baby F. The force of friction is a force that opposes motion. So when you slide an object against another object, the force of friction is a force that pushes against the motion of the object. So in this case here, the girl is pushing to the right with a pushing force, which means that the force of friction opposes it. And it always acts in a direction to oppose relative motion. So this is something that sort of makes sense, right? If you're driving a car, the force of friction opposes the motion of the car. It's a force of contact. F subscript F. Another force that's related to this is air resistance, which we won't do a lot, but it is important to understand. F air. F air, fair. F air is a special type of frictional force that opposes motion as you're moving through the air. So friction in itself is only when you're physically in contact with another object. Air resistance applies when an object is moving, when air is opposing an object's motion. Fair. This one's very messy. We probably won't do much of air resistance at all, but friction we will do a lot of. Tension force. The Boomerang fair combos with Young Link and Smash Bros. I'm trying to think. I don't really. I think I see what you're saying. Okay, so tension. The force of tension. This is probably one of the toughest forces to understand. So any single time there is a string, rope, cable, or wire, any single time when there are one of these things that's being pulled, there is the force of tension. Every single time there is a force, a string, rope, cable, or wire, there is a tension force. And that tension force is the force that, you're right, is that the rope, string, cable, or whatever exerts when it is being pulled. So in this example here, we have a sugar packet thing that's being pulled downward by gravity, right? Because it's on a string or rope, there is a force of tension pulling it up. We call this force tension, and we label it F subscript T. But this is probably one of the hardest forces to understand, and you will see why. It's because tension can get very messy very quickly. Okay, and then so this is sort of a quick summary of the forces. Yeah. Oh, I forgot one more thing. There is an applied force called FAP. Oh God, no. I should not have said that. There is a applied force F. That was not intentional. I'm really sorry. That was intentional. That was not intentional. So there is a force applied. That is basically the force that you apply as a person or an object applies. So like an engine, a car engine, right? That's a force. That's an applied force. If you pushing an object, that's an applied force. If you are throwing, well, no, throwing an object's not an example. But like that's a force that you physically, and like external force that's being applied. So that is an applied force. We can call that F subscript applied app. There's a tension force, F subscript T, force of gravity, F subscript G, force of friction, F subscript F, fair force, F subscript air, and then normal force, F subscript N. Okay, so those are the forces that you're going to do. Okay, so due to timing, because we only have 20 minutes left, and I do want to give you a chance to start your stuff. What I'm going to do is I'm just going to do this on the board for you, and you can just write it down, and I'll try to explain it for you, so that way you'll sort of understand what I'm saying. Okay, so an acorn is falling from the tree. So an acorn is falling from the tree. An acorn is a box, and the box is falling down. Okay, so because we're neglecting air resistance, that's it. That's your free body diagram. Pretty simple. Okay. So a student rests a backpack on a shoulder. So if you put a backpack on a shoulder, right, it's not really accelerating. Backpack always has the force of gravity. F subscript G. And because it's motionless, it means that there needs to be an upwards force equal and opposite to the force of gravity. So I guess so. I would call this an applied force, but because it's a backpack, let's just call this an applied force. So the backpack is the strap is applying a force to keep the backpack up, and that's equal and opposite to the force of gravity. So the net force here is 0. And then last but not least, there is a box being pushed to the right to move it across the force with the rightwards acceleration. Okay, so this is probably the hardest one. We want to consider frictional forces here. So I'll try to do this as detailed as I can. So the box is being pushed to the right. So the first thing we want to do is let's identify the forces that are going to be present here. The force that is always going to be present is the force of gravity. So right off the bat, you can draw the force of gravity. Now, is the box accelerating up or down? No, we're just pushing to the box to the right. So because it's not accelerating up or down, we know that there has to be a force that opposes the force of gravity. So we know that there has to be some sort of force opposing it. And because it's on a table or a ground, there's a normal force being applied up that's equal and opposite to the force of gravity. Now, the box has an overall rightwards acceleration, and we're pushing it. So we are going to be pushing it with an applied force. Let's call this applied. So we are pushing the box with an applied force of FAPP. And then last but not least, we're actually considering frictional forces. The thing is, because there is an overall rightward acceleration, it means that the net force is not 0, which means that whatever frictional forces occurs here has to be a little bit smaller than our applied force. Otherwise, the net force is 0, and then the box will be moving at a constant velocity. But because the constant velocity is not, the net force is not 0, because the acceleration is not 0, the net force can't be 0, which means that your applied force should be greater than your frictional force. So that's in general what a free body diagram should look like. Right? It doesn't. Yeah, I'm hoping that this isn't too complicated. Like the idea, the principles behind this is not too challenging. The hardest part is identifying which forces are where, and identifying how big each force should be. Okay, so before you, okay, so what are we doing today? So we don't have a whole lot of time yet, but that is enough time for you to get started. So on the main assignment we're working on today is there are free body diagram practice problems. These are going to be a bit of a rinse and repeat. They are a little bit repetitive, but it's the reason why is I want to give you all practice with these problems. They should not take you too long. You should be able to move them pretty quickly. Usually, so there is an interactive portion of it. Okay, so here's the assignment itself. So there is an interactive portion of this that there's a little physical tool that you can use to draw free body diagrams. What I will do is I will say that this is what I will say is that it is optional, just because I want to give you as much time as possible. It is optional, but if you are having a hard time with the actual word problems, then I would recommend doing the simulation. But I will say that this is optional. Otherwise, I will let you get started. Let me know if you have any questions, and then we'll have the rest of the period to work on this. I'm hoping that you'll be able to get through maybe 3 or 4 of these at least. Yeah. So if you want to do the simulation, it is helpful, and you will get answer checks. Should you finish the exit ticket? Yes, do finish the exit ticket. Yes. On your graphic organizer, there is an exit ticket question. It'll look very similar to one of the questions we just did. So just do that really quickly and then submit it and then move on to the free body diagram practice problems. Another thing I will say is the wording of these problems is very important. The wording is very important. Read each problem very carefully. Make sure you're understanding what is going on. Yeah. Other than that, if you have any questions on what to do, just let me know. Otherwise, I will stop talking and let you do your thing. okay, so let me also go over one thing. I think I might not have described this perfectly. Tension is a pulling force from a rope, string, cable, or rope. Only those four things. However, an applied force can be pushing or pulling. So, for example, if I'm pulling a box, right, there's not going to be any tension there, but I am applying a force. So your applied force can be pushing or pulling, anything that's really just any force that it doesn't really fit any of the above. It's like an external force. A tension force is only a force from a cable, rope, and any sort of connection. Another problem is that is pulling a string. Pulling a string will be tension. It won't be applied. It'll be tension because the tension of the string is causing something. Yeah. So if you're pulling a string, the string it's a tension force because the string is the force that is pulling it. Um, well, so reins on a horse. Yes, yes. This can get very complicated very quickly. So I just want to be, yes, in general, yes. This can get very complicated very quickly, especially when it comes to trains. I don't know if we will do this in this. I don't know if we have time, but trains are connected by like the little things. I don't know what they're called, but those things is an example of tension actually. And so what will end up happening is you have tension pulling both ways and can get very complicated very quickly. So I just want to say in general, tension is sort of thingy with related to string, ropes, cables, and stuff. But it can get very complicated very quickly. I think these problems themselves aren't that complicated yet. We will not skip that part. We will not skip that part. It is very important. We will not skip that part. But we won't get to it yet. I want to give you a little bit of a. Okay, I really made a big doo doo. I made a mistake here. So the backpack, I sort of realized the backpack itself. I sort of mixed up the context. So the backpack is being pulled down by gravity, but what's keeping the backpack up is your shoulder. It's not the strap is keeping it up; it's your shoulder is keeping it up. So and the shoulder is applying a net force as a normal force on it. So on your backpack, right? It's being pulled down by gravity. So I actually have a backpack right here. I'll show you. Okay, so I have my backpack, and then I'm 21 jump shooting, so it's one shoulder. Right. So the backpack is being pulled down by gravity, but my shoulder is applying a normal force upwards. And so this is actually a normal force and not an applied force. So I made a mistake here. So this should actually be a normal force. And that's something you should consider when you're looking at objects being suspended or something, is whether or not something is actually physically keeping it up. And that's very important. So I messed that up. So So if you are looking at the parachute, for example, I think you answer your own question. So applied force is generally a force that it's like a doesn't fit any of the criteria above. It's like a force that I'm physically applying. Um, so that's something you should consider. So am I physically applying that force, or is it an external force? So for the parachute, you should think about, am I applying an external force, or is it just a force that is occurring? Okay, so we've got a minute left. Unfortunately, I didn't give you as much time to do stuff as I would have liked. That's that's what happens when you are make a lot of mistakes. Okay, so I'm hoping that we can finish the free body diagrams by next Monday, Tuesday. I'm still gonna keep the due date, but if you feel like it's excessive or you feel like you need more time, just let me know. Because you're just drawing diagrams. And I guarantee it's because you're drawing diagrams. Hopefully it won't take you too long, no more than 20 minutes. But otherwise, yes, your homework is to finish the forest data analysis and then the free body diagrams. So yeah, do both before next Monday. Other than that, I have office hours today and tomorrow, 2:40 to 3:40 if you want to come by. Otherwise, I will see you all next Monday. So yeah, have a good one.
Thank you.
Thank you.
Thank you.
Thanks, Mr. Hu.
Thank you.
Bye.
Bye. Bye. Thank you so much.
Thank you. Bye.
Mr. Hu?
Mhm.
For the force data analysis, do our final revisions have to be in by Monday?
No.
Or it's
It's like a first draft.
Oh, okay. Perfect.
Yeah, because we're gonna do a lot of we're gonna do I'm gonna give you feedback and you're gonna do some self-assessment too. So there's just gonna be a lot of revisions for it. So definitely not.
Okay.
It should be like a decent first draft.
Okay. Thank you.
Yeah.